Now that we have the D-peptide in complex with the L protein, we now want to look at mutations, specifically point mutations, that are going to increase the predicted binding affinity of our D-peptide for our L protein. Specifically in this case, we're going to apply the design technique of inverse alanine scanning. So what we're going to do here is we're going to do two things. We're going to look at the maximum contribution that a single residue can make to predicted binding affinity, and then we're also going to find the maximum flexible set for these point mutations. So let's walk through exactly how to do that. Before we jump into that, I'm going to do a little bit of organization. I'm going to make a directory called alanine scanning. And we're going to need to do this alanine scan for each residue on the peptide. In this situation, our peptide is 6 residues long, so I'm going to make a directory. I'm just going to call it residue 1. And I like to organize my directories with 2 ensemble subdirectories where all of my structures will go, and I will just copy that for each of the residues on the D-peptide. Great. So now that we have those, we're now going to jump over to Pymol for a quick visualization. So quick reminder, this was our output from the minimum flexible set. This is our D-peptide in complex with our L protein with steric clashes alleviated. So let's again visualize these a little bit better. Show as licorice sticks. Again, I like my peptide to be in purple. It's a little bit easier to see. So we're going to start here at this glycine 45 on the N-terminus. So in inverse alanine scanning, this is inspired by experimental alanine scanning. We usually only mutate one residue to alanine somewhere on the chain, and then you measure the change in the change of Gibbs free energy to see how a specific residue contributes to binding affinity. Inversely, for inverse alanine scanning, what we're going to do is we're going to mutate this entire peptide to alanine, except for this residue on the N-term. And we're going to mutate this N-term residue, instead of to alanine, to all 20 amino acid identities. And this will help us understand what the optimal mutant is for this specific residue, given optimal flexibility. And the reason it's optimal is because, in reality, this peptide isn't going to be all alanine, but it will allow for optimal translation rotation. We're also going to be able to afford lots more flexibility on the protein because we're focusing in the region around this one residue. So in order to do this, let's look at glycine 45. I'm going to click this residue. I'm going to highlight the entire protein. I'm going to right-click, Actions, Find any contacts between chains within 4 angstroms. Now, I'm going to do 4 angstroms just because that's what's in Pymol. It's easily visualized, but you're more than welcome. In fact, it's a good idea to have a wider search space given your computational limits. So if we look at here, we're looking at this glycine. Residues coming off like this, and we have contacts here. This residue looks like it, so it's contacting H301 that's within 4 angstroms here, and those measurements are shown here. So size about 3.9. We have some 2.7 angstrom range or 3 angstrom range. So when we're allowing lots of flexibility in this ligand, we want to make sure the cysteine is flexible so that it can accommodate, and we can accurately assess many point mutations on this residue. So that's going to be flexible residue H301. So we should note this somewhere. So I've set up an Excel file that has the output of the minimum flexible set, again using match 4 with the original sequence. I'm saving my results from minimum flexible set, and the residue we're setting as flexible again is H301. I save that. I'm then going to repeat this process called round 2 here, and I've already done that here, and that's going to be histidine residues 301 and 341. Again, after the N-terminus, it's going to be the next residue, glycine 46. Same process, actions, find any contacts, then 4 angstroms, and we're going to list those residues that are in contact. Now that once we've done that and we have our list, we're going to go back over to DexDesign. While I'm organizing this directory, I've also imported the output of the minimum flexible set, which was available in my ensemble directory. I'm just going to rename this to minimumflexibleset.pdb. Now I have that here, and I'm just going to copy that into one of the residues. The reason I'm not going to copy in all the directories, we're going to start with residue 1. I'm going to make again, an osprey molecule using this PDB, which I'll then copy over to the remaining because we don't need the PDBs after we've created the mol. So let's go over and start the interface. Again, we're going to start back from our preparation phase, file input B, PDB, alanine scanning, and let's start with residue 1, that interim. Let's open this PDB. File prepare. Let's mark this D-peptide as being a D-peptide once again. We've already run this through Osprey, so these should all be correct. It doesn't hurt to double check to make sure we don't have any duplicate atoms. Nothing's missing. As expected. Missing. Let's go ahead and clear. Place bonds. And these all should be correct. We'll do this just to double check. Clear and re-add hydrogen bonds. File, and let's go ahead and save this Osprey molecule. And this will appear as mfs.omol in our directory. Let's go ahead and close this. And again, we're going to go to File, New Confirmation Space. And now we have that OMOL file ready for design. We're going to hit Open. And now we have this visualization. Can hit Edit. And again, we're going to go to our confirmation library, add L amino acids for our L protein. We're going to add D peptides for chain A, our D-peptide. Last time in the known flexible set, we skipped over mutation, went right to flexibility. This time we're going to hit the mutations menu, which will pop out here. So we're not interested in inducing mutations on our target, chain Y, but we are on our peptide, chain A. So we're going to hit chain A, we're going to click Add. This will open our mutation menu. So keep in mind, and feel free to click in between PyMol visualization and here. We're starting with glycine 45, which will be our first residue we're doing our inverse alanine scan on. So we're going to hit glycine 45. We're going to go over to mutations. What we're going to look at here is all the identities that we've assigned to this residue. So it's showing the wild type is glycine, and we're going to check this at all 20 amino acid identities. So we're going to click alanine, and we're going to go all the way through and click all these. So we've checked all 20 amino acids, hit close, and now note that we have made mutations, made mutational assignments to glycine. We're now going to mutate all the other residues on that peptide to alanine. So let's hit add, go to glycine 46, mutations, alanine, and note that we can uncheck this wild type here. Hit close. That's one sequence for that glycine. And we're going to repeat this process for every residue on that peptide. So we're on the chain, hitting add, residue, alanine, unchecking that wild type. So 1, 2, 3, 4, 5, 6, these are all alanine, and we're doing our scan at glycine 45. Now we've assigned all those mutations, we can close this menu. Gonna go back to edit, and we're again gonna open up our flexibility menu. So let's talk about our A first. What you'll now notice is that we have mutable position assignments here, but you'll notice they don't have any confirmations. So we actually need to set flexibility for all these mutants. So let's start with glycine. If we click glycine here, this edit will become highlighted. We can hit edit, actually go through and individually select confirmations for each of these assignments. I'm just going to select all, and notice that all the confirmations are now selected. Close this menu. I'm going to go through and do that for each of these alanine mutations on the remaining residues. So hitting again, clicking the residue, clicking edit, and then select all. Also click it, select from here, edit, select all. Last residue, leucine, edit, select all. Close this menu. And you'll now note that the combined confirmation has gone to 0 to 203. So note that we're on our D-peptide, so let's go ahead and set our translation rotation while we're here. We're going to hit add. Make sure translation rotation is checked. Close this. It's now highlighted. And our flexible residue was this histidine here, histidine 301. So we're going to go into our interface, hit chain Y, which is our protein, add. Again, our flexibility menu will open up. Histidine 301, we'll hit close. And note that our combined conformations have increased to 5,000. We've now assigned conformations, assigned our mutation flexibility. We're now ready to save the conformation spaces, compile, and run the K-star score. We'll do the exact same thing we did in the minimum flexible set. Save. We'll call this, I'll call this round 1 for residue 1 complex. Split again, round 1 protein. And then round 1 ligand. Compile the conformation space for the complex. And then we're also going to go through and compile the conformation space for the protein and the ligand. And just like for minimum flexible set, we will run the K-star algorithm. So once you run the K-star algorithm, you'll get an output that looks like this for the inverse alanine scanning. So what I've done here is I've organized some of this data. This is the output for the minimum flexible set. And I've highlighted the mutant here that produces the highest predicted K-star score for the interim. Note again, we're looking at flexing histidine H301, remutating glycine at position 45 on the D-peptide. We have our sequences here. We are looking at the wild type. So if we look for the wild type, so it's 45 here. Note again, this is lowercase. And all the mutants are in uppercase, so glycine, valine, tyrosine, all these mutants are uppercase. So our wild type conformation is a predicted binding affinity of 8.46, our K-star score of 8.46. And then our mutant as a K-star score of 9.44, and that is for the mutant arginine. So we'll note this, I've highlighted here in the Excel sheet, and we'll repeat this process for the remaining residues on that peptide. So we'll repeat this for G46 through leucine 46, 47, 48, 49, leucine 50. So I've gone through, I've performed the inverse alanine scanning on all of the residues on our D-peptide, and I found the point mutations on each one that is predicted to increase the binding affinity. So note here, glycine 45, arginine. This number here is the difference between the wild type and the mutant. With the flexible residue of H301, this is again glycine arginine. So I found here the 3 greatest increases in K-star score. These occur at isoleucine 48, mutated arginine, serine position 49, mutated histidine, and then leucine 50, mutated to tryptophan. These correspond to a difference between wild type and point of 1.1, 3.1, and 1.4 with these flexible residues. So the question is, how do we take all of this mutant data and flexibility data and perform a combinatorial search? So typically we'll do mutants on all of these residues. I'll just do these 3 for the point of the demonstration. But the question is, we have quite a lot of flexible residues here, and the question is, how do we actually reduce them down? You'll note over here, I've actually already found the reduced flexible set. So what I'll show you is, let's look, for example, at residue 50 leucine mutated to tryptophan, which is predicted to increase the K-star score by 1.4 relative to wild type, and that has flexible residues L291 and histidine 311. So what I'm going to do is I'm going to go to where I calculated the K-star score, and I'm going to find that ensemble output and look at that ensemble in Pymol. So I'm currently in the directory for position 6. This is the C term, the residue L50. I'm going to navigate into the ensembles directory, down one more where the outputs are, and you'll notice this file is much bigger because compared to the minimum flexible set because of all the mutants. And we want to find, in this case we've noted leucine 50 mutated to tryptophan. So we're going to find that file, we're going to find that PDB, so it's leucine 50, scroll down, located here. So I'm looking at position 50, leucine to tryptophan, and this is the PDB file. So I'm going to download this PDB file and open it up in Pymol. Okay, so again, I've downloaded this. Visualize the secondary structure if you like with Command DSS. And I'm going to just visualize this for a moment. So I'm actually going to look at all the side chain residues, show as licorice sticks, and again, put my ligand in purple. So what I'm going to look for here is a change in position of each of these flexible residues. So in the K-star run, we flexed residue L291 and H311. So let's hit play. We're going to be looking at residue L291 and H311 here. So you'll note two things. Note that this histidine is changing quite a bit. I mean, this D-peptide is changing quite a bit as well, changing conformations. We certainly want to keep this flexible in our combinatorial search because it's moving so much. Note that the side chain is moving quite a bit, and this is certainly something that we want to keep flexible in a further search. However, if we come over here, this is that L291 residue. This is a smaller conformational change. We actually overlay this with the wild type. So I've imported the wild type, and I want to visualize this. I'm going to pull out peptide, overlay these licorice sticks. Again, looking at that residue. Residue L291 in particular is moving very slightly relative to its wild type. This could be important, but for a combinatorial search, we're really looking for large changes in our conformation, specifically something like we're seeing on the histidine where it's actually changing the rotamer identity. So this is something we're going to prune from our search space and our combinatorial search, and we're going to look at this. We're going to look at these ensembles for each one of our ensemble outputs from Inverse Alanine Scanning. So each one of those point mutations that are predicted increase binding affinity. So I48 to R, S49 to H, and we're going to look at each of these residues and their ensembles. I've now reduced that space to just 2 flexible residues relative to how much they're flexing in the ensemble output. So now that I have my reduced conformational search space, I now need to do one final K-star run for Inverse Alanine Scanning, which is going to be this combinatorial search. So let's do some more organization. I'm going to go to the DexDesign folder. I'm going to go into alanine scanning, make a directory called combinatorial search, and again, I'm going to organize my ensemble outputs like this, and change it to that directory. I'm going to copy over the inflexible set OMOL file so I don't have to re-prepare that. And I'm going to now do the combinatorial search. So let's go over to the interface. Start that up. Hit File, New Conformation Space. I'm going to go to DexDesign, Alanine Scanning, Combinatorial Search, Open. So all I've done is I just opened the osprey molecule for the minimum flexible set. I'm now going to use that information I've gained from Inverse Alanine Scanning to do a combinatorial search, reduced conformation and sequence space. Prepare this in the same way we have already. Adding L-amino acids for our protein, D-amino acids for our peptide. And our mutants, again, are noted in the Excel sheet, so I'm just going to refer to those. It's going to be 48R. It's then going to be S49 to H. Again, I want to check both that wild type and the mutant residue to ensure that these are productive. We look at these simultaneously. Then L50 to W. All right, so I've set all those residues flexible. Again, just as before, I go to our flexibility residues, make sure all of these mutations have flexibility. Also going to put again, translation rotation on our peptide ligand, and I'm going to set residues L348 and H311. These are the persistent flexible target residues that moved significantly during inverse alanine scanning, so L348, H311. Here. And just like before, I've now constructed the conformation space on a reduced conformation space. I'm going to save these conformation spaces, compile, and then assess the K-star algorithm outputs.